Okay, we're ready to start. We have a talk by Andrei Barvinsky and we'll speak about Horava gravity. So please start.
Okay, thank you very much. I believe I can just sit here, yeah?
Yes.
Okay. Hello, everybody, and I'd like to talk today about the project that was research that was conducted for a number of years by the people who you can see here. So this was a collaboration with Diego Blas, Mario Ferravalle, Alexander Kuprov, Sergei Siderikov, and Christian Steinmetz. So the people who are now basically dispersed all over the world. I believe this is this project has reached a certain point when we can actually share some results and some methods regarding the properties of Horava gravity and its locality, unitarity, and renormalizability. Of course, I would say that this model actually solved the problem of physically reliable existing in nature quantum gravity theory, which is consistent and in the ultraviolet domain. Because from the viewpoint of observational status of this model, does not fit the properties necessary observationally confirmed properties of low Einstein gravity theory. But as a model, it's very interesting and it is worth considering it. And moreover, it actually serves as a rather interesting playground for new methods, calculational methods of quantum gravity and quantum field theory in general, when the usual conventional Feynman diagrammatic technique for the calculation of loop corrections can be replaced by a more powerful method of heat kernel and the method of the so-called universal functional traces in background field formalism that was developed actually rather long ago. But what I'm going to talk about today may be the first example when this method actually becomes really indispensable, because by the methods of the usual Feynman diagrammatic technique, these results, that is the beta functions and renormalization group flows for the case of 3+1 dimensional Horava gravity theory would be simply impossible to obtain because of calculational difficulties. Well, anyway, this is the set of questions that I'm going to discuss here, and here you can also see a number of publications where these results were presented. And so let me then go over to the problem of renormalization of Horava gravity. You know very well that okay, this is just wondering. This has appeared. This black line appeared, strip appeared at the top of the screen, but I believe it. Okay. So you know very well that usual Einstein gravity theory, general relativity, is not renormalizable. And the attempt to generalize it to the case of renormalizable gravity theory, when all the ultraviolet corrections, infinities can be absorbed into the redefinition of coupling constants by adding the higher curvature corrections to the Einstein term in the action. This is not a resolution of the problem because of the presence of high order space-time derivatives in the Lagrangian. The theory starts suffering from the presence of ghosts. And therefore, there is no good unitary interpretation of the theory. And the question arises, is it in principle possible to somehow circumvent this difficulty of the arising ghosts? And you know very well that due to Peter Horava, due to his work of 2009, there is the idea how to do this by using certain knowledge from the physics of condensed matter theory. Actually, this is the idea due to Lifshitz to consider the theory where the spatial derivatives in the model are taken of higher order than the time derivatives. So that if you consider the action, say, in the quadratic approximation in the fields, and replace, just leave the kinetic term of the action as usual, quadratic and first order derivatives with respect to time, but then replace the usual second order spatial derivatives by the, say, by the Laplacian to some power z, then what one has, of course, is that the corresponding Feynman diagrams, they get much better convergence because, roughly speaking, the convergence of the Feynman diagrams is determined by the highest power of space-time derivatives sitting in the inverse propagator of the theory. And then there is also, when you do this, of course, you have a violation of Lorentz invariance, because you, of course, you can see that spatial derivatives are entering this section with higher orders. And moreover, the theory acquires like this. The theory acquires additional global symmetry, which actually generalizes actually the notion of usual physical dimensionality in the theory. So this theory, which we have here, the simplest toy model theory, it has a symmetry under the rescaling of the spatial coordinates and the rescaling of time coordinates by the parameter which has different powers in spatial coordinates and in the time variable. And it is possible to show that if you consider this parameter z more than 1, then starting from actually z equal the number of spatial dimensions, this theory would be renormalizable if you include the corrections, the interaction term, which basically has a similar structure in the in derivatives, the same maximum second order in time derivatives and the same order in spatial derivatives. So this exponentials of this parameter b is usually associated with the generalization of the notion of physical dimensionality. So now we have the dimensionality of spatial coordinate 1, but the dimensionality of time coordinate now is not, sorry, x, the dimensionality of x is -1, and the dimensionality of time coordinate now is not -1, but just -z. So this idea actually can be extrapolated from this theory, where actually Hij not necessarily the metric perturbation variable of the gravitational model, but it can be just a scalar field. But this idea can be actually extrapolated to the case of gravitational models, and the structure of this generalization looks very transparent if you consider Einstein gravity in terms of the so-called Arnovit-Deser-Misner variables. That is three-dimensional metric, well, d-dimensional metric if we work in d+1 dimensional space-time. So the d-dimensional spatial metric, shift functions, and the so-called lapse function. And then it is easy to show that if you consider the class of not general diffeomorphisms, but restricted class of diffeomorphisms, the so-called foliation preserving diffeomorphisms, then under the diffeomorphisms of such a form where spatial coordinates are transformed generically as new coordinates as functions of all spatial coordinate and time, but the time coordinate transforms only as a function of the original time without any spatial dependence. Then with this corresponding ADM decomposition of the full d-dimensional space-time metric, one can construct the action of the theory, which is invariant under the following global transformation. So you see now this parameter of rescaling is denoted by lambda, and correspondingly we have these types of rescaling of x, t, ni, and gamma ij. So this means that the dimensionality of spatial coordinate is constant and equals -1, but the dimensionality of time is -z. Shift functions have the dimensionality z -1. That means that it transforms by this law, and the dimensionality of gamma of three-dimensional metric is 0. So this type of invariance is usually called anisotropic scaling invariance, which means that it is not isotropic with respect to time and space. If now we can consider the extrinsic curvature of spatial slice, which of course will have the dimensionality z, and with these definitions, one can construct the action which has such a form. You see, this is the kinetic term, very similar to what we have in Einstein theory. The only difference is that there is a generic arbitrary coefficient parameter lambda in front of k squared. K is a trace of extrinsic curvature. And then there is also generically very non-linear potential term, which depends only on spatial derivatives of the three-dimensional metric. And this spatial not containing time derivatives potential is usually constructed as an expansion in powers of spatial curvature invariance with respect to the d-dimensional spatial diffeomorphism. That means that this nu of gamma is actually constructed starting from usually generically from the cosmological term, Einstein term, but three-dimensional Einstein term, and then quadratic and higher order terms in powers of three-dimensional tensor, Ricci tensor scalar, and so on. Now, there is a possibility actually to consider a more restricted class of such models where the lapse function is actually considered to be constant and equal to 1. This is the so-called the class of projectable Horava models. And then what follows, we will basically consider this projectable case because, as we will see, we can prove the renormalizability at a rather rigorous level. We can prove the renormalizability, UV renormalizability of projectable Horava gravities, but for non-projectable ones, when n is a non-trivial function of both space and time, this is thus far this goal has not yet been reached. So we cannot say
Andrei,
about
sorry.
the normalizability of non-projectable models.
Let me interrupt you.
But in the non-projectable models, of course, the plethora of all possible curvature invariants which contribute to this potential term of the Lagrangian is much bigger, and it involves in particular also the gradients and higher order spatial gradients of the Lebesgue function, which becomes in this generalization a generic parameter.
Andrei, sorry.
Generic function of space and time.
Do you hear me?
Now, if you consider actually, say, in four-dimensional case, if you consider the theory in the on top of the flat space background, then one can easily derive the dispersion relations for the physical modes. And the physical modes, they will have such a dependence of their frequencies, that is zeros components of the d-dimensional, d+1 dimensional space-time momentum. Well, in this particular, for this particular equation, dispersion relations, d is just 3. Well, in case if you have d different from 3, then of course the highest power of the spatial momentum becomes higher. So this highest power is actually 2z, and as long as z, the parameter z equals d, then this is 2d. D is the number of spatial dimensions here. Well, okay, let's see.
What was there a question? Because for some reason.
So I wanted to ask some question. Could you go to the previous transparency?
I didn't get it. Get to the previous slide. Okay. Yeah.
Okay. So explain, please, structure of action S. Does it mean that you fixed the terms Kij, Kig, and all other terms are constructed on the base of symmetry?
So you have the square of Kij.
Is it fixed?
Sorry, say it again.
You introduce some symmetry, some dimensions of the objects. Then the first term in the action, Kij, Kig, is fixed, and all other terms are constructed on the base of this symmetry. Is it true?
Well, yes, of course, we demand that the dimensionality of all these terms is the same. So it's, you see, it should be, the dimensionality should be such so that under this anisotropic scaling, the transformation of this Lagrangian of this factor would be cancelled by the rescalings of type and x.
Is there any arbitrariness in the potential term?
Well, basically the potential term, its highest order in the curvature is chosen so that to provide renormalizability, so that the highest order should be determined by the dimensionality of space.
Okay.
In 3+1 dimensional case, this is the highest order term is cubic in the curvature.
Okay, thank you.
And in 2 dimensions, in 2+1 dimensions, this is quadratic in the curvature, and so on. Okay. So getting back to dispersion relations. Okay. Yeah, getting back to dispersion relations, I should mention that these relations show that okay, it's low. They show that actually the low energy limit of this theory is different from Einstein gravity. So we can believe, for example, if we try to accommodate, if you try to make this theory consistent at high energy level and renormalizable, but then if we can go over to the low energy limit, then of course we can disregard high powers of the spatial momentum, and then we have a fundamental problem which actually shows that in the low energy domain, this theory is hardly consistent with general relativity because, as you see, irrespective of the sign of this arbitrary coupling constant eta, which is basically the usual gravitational coupling constant, either transverse traceless sector of this theory has a tachyon, or the scalar sector has a tachyon. You cannot get rid of this. There are, of course, certain ways to circumvent this problem, but in any case, these attempts, they are almost completely ruled out by either the strong coupling, impossibility to apply this formalism within the below the strong coupling scale, or some other difficulties. So basically what I will consider the quantization of this theory and the consistency of this theory in the high energy domain, and we'll try to justify that as a UV theory. This is a kind of a complete theory, UV complete theory. So, but in order to do that, we have to actually to circumvent a number of technical problems, and let me basically briefly explain how these problems arise. First of all,
can you comment a bit on degrees of freedom?
Well,
so you say there is spin 2 and scalar.
Yeah.
But how do you define like spin 2 and scalar if Lorentz invariance is broken or it's not broken?
Well, of course, this is just the usual decomposition of Hij in irreducible components in the usual sense. Transverse traceless, vector, scalar components. This is the same.
So you cannot identify.
This is not you see, this is transverse traceless is actually in the three-dimensional case. Therefore, you just don't care about the violation of Lorentz symmetry, because we still stay within the usual three-dimensional rotation symmetry, and then we have this.
So you cannot say these frequencies correspond to spins. It's only independent independence oscillations.
Dependence what?
You cannot say anything about spins. It's some three-dimensional decompositions, nothing more.
Well, this is just a second-rank tensor, if you like to call it spin 2. But if you would object that this is a wrong terminology, then you're welcome. I agree. This is just the case of spin 2. I don't have any intention actually to generalize this case to the higher spins, and that's it. That's everything I can say.
Sorry, I also wanted to clarify, like, as I understand, like complete diffeomorphisms are broken. To me, usually this means that there are some extra degrees of freedom, which are usually ghosts. Like my expectation, like if you try to do some random things in manifestly, let's say Lorentz covariant case, like whatever, like if gauge symmetry is broken, usually you gain ghosts. And here you have only part of diffeomorphisms.
No, there is no ghosts here. You see, ghosts here could have arisen actually from different sources. First of all, these are high derivatives in time, but we don't have time here. Yeah, high derivatives in time. And if you consider in this theory the physical excitations by solving the constraints, and then you will see that there is no ghost here, because in Einstein general relativity, you see, well, anyway, this is just the fact of observation. You can construct the physical sector, and you will see that there is a scalar mode which is not a ghost one. You see, this is not a four-dimensional conformal mode. This is just a scalar mode in Hij in three-dimensional sector of the three-dimensional metric, and therefore This is the situation is somewhat different from Einstein's theory. Okay, so again, renormalizability, of course, depends on the power counting, and the power counting in such Lifshitz type models actually is determined in a rather kind of non-trivial way. You know that in the usual Lorentz invariant theory, actually the convergence, the degree of divergence of the Feynman diagram is determined by physical dimensionality of the integral. In case of the Lifshitz series in Horava gravity, actually the degree of divergence of the of these diagrams is determined by the scaling dimensionality. For example, in these models, you have the type of the Feynman diagram looks as it is here. You see the power of k is different, but the dimensionality of omega is different from 1 in contrast to the usual series. And the overall power of divergence of this diagram is actually determined by the scaling dimensionality, different from physical dimensionality. As I already mentioned, the critical value of the parameter z, which makes the theory renormalizable, equals d, the number of space-time dimensions, which means that in, say, in 2 dimensions, that is 2 + 1 dimensional theory, this potential should be chosen in such a way. It is at maximum quadratic in curvature, and of course, in case of 2-dimensional spatial metric, we have only one invariant, which is just the curvature scalar. There is no independent Ricci or Riemann tensors. In 3 + 1 dimensional theory, you have the structure of this potential is more complicated. You also have cubic terms. I do not write it explicitly here. They will appear a bit later. Now, this is actually very naive statements about and trivial statements about how the degree of divergence of the diagrams changes if you go from Lorentz invariant to Lorentz non-invariant series having this anisotropic scaling invariance. But actually, the situation is trickier in the following sense. Things are not so simple because simple arguments of power counting is really not enough in order to provide the renormalizability of the theory. Yeah, okay.
I have a question about the previous slides. I actually don't really understand how, why the one about the power count, right? So I do not really understand how changing the scaling dimension of the, say, omega like the actual convergence of the for a fixed integral is a number or it's not a number. How does changing what we call dimension changing the fact of the
Well, the simplest thing to see it is the following. You just, for example, in this integral, you can replace the integration variable omega by something like omega equal rho to the power z. And then you will see that the convergence of this integral will be determined by this recipe for the counting of the degree of divergence. And this will be just the scaling dimensionality of the integral. Yeah, but after this change of integration variable, the powers of this new variable rho, say rho, will become the same as the power of k. So rho will play the role of omega 0 in the conventional theory.
Yes, the divergence is governed by power of k.
Yeah, if you like. Yeah, if you like, you can say it like this. Yeah. But the problem is that actually things are not so simple in the following sense. generically, if you go make the transition from usual Lorentz invariant series, where the typical Feynman diagram looks like this, you see here in the denominator, you have just the powers of the 4-dimensional p squared. Yeah. Well, I mean space-time Lorentz invariant p squared, d-dimensional in any dimensionality, in any d+1 dimensionality. Yeah. Now, in case of Horava gravities, what you have the following. You have integration over corresponding omegas over the corresponding spatial momenta. And here in the denominator, you have the combination like this. And in this combination, you have, so omega capital and k capital. These are some linear combination of independent loop momenta in this expression. Now, what is important that these coefficients here, AM and BM, they should be both either positive or negative, because if they are of different signs, then actually this naive power counting arguments based on the notion of anisotropic scaling dimensionality, anisotropic scaling will not be applicable. And therefore, in order to be able to apply standard theorems on the renormalizability of the model according to these power counting arguments, one should provide this property that this both coefficients here, the coefficients in the inverse propagator of the theory, they both of the same sign. But they depend on the choice of gauge, because this is a gauge theory, local gauge invariant theory, invariant with respect to spatial diffeomorphisms, d-dimensional diffeomorphisms. And therefore, if you consider generic gauge, then what will happen that in general, these coefficients, they might get whichever signs you will have due to some unsuccessful choice of gauge.
Let me interrupt you. Sorry. Andrei, do you hear me?
Yes, Joseph.
Let me understand your statement. We usually understand that if we make subtraction of subdiagrams, we obtain the local divergences. Now you say it's not enough?
Yeah, absolutely, absolutely. If this property is violated, you will get kind of remaining non-local divergences after the subtraction of the corresponding local counted terms generated by lower order loop corrections.
It's fantastic.
This can be proven more or less rigorously just by considering getting into the details of this procedure. I cannot really expound these details here. It would be impossible.
Okay, I believe you, but it looks like very fantastic.
Well, anyway, this is the status of this problem. So the first step in the proof of renormalizability was the task of finding such a class of gauge conditions that would provide the positivity of both coefficients here. And this class of gauge conditions was found. And I will not, well, this slide, I will not really present this gauge condition explicitly, but in principle, the structure of this gauge condition is as follows. You have the gauge breaking term, which is basically the square quadratic form in the gauge condition functions with some gauge fixing matrix. And we have to actually consider as this gauge fixing matrix a rather non-trivial, non-local, in principle, non-local. I'm sorry, the inverse is non-local, but the inverse of this matrix, which is sitting here, is actually local, but it involves higher order derivatives. And the structure from the viewpoint of three-dimensional rotation invariance, this structure is more or less unique. You see it is given here. And this gauge condition actually provides this property which is necessary for this cancellation of non-local corrections in the higher loop orders by the lower order loop contributions. So in this sense, the necessary properties of the Bogolyubov-Parasyuk-Hep-Zimmermann renormalization scheme become here enforced. And in this way, it is possible to show that projectable Horava gravity theory is actually renormalizable in any D. So there exists actually a two-parameter class of gauge conditions, and these parameters here are sigma and the parameter psi sitting in the definition of this gauge fixing matrix. These two-parameter family of gauge conditions, they provide renormalizability. Another problem, this is a problem of gauge invariance of counterterms. Well, in principle, this is a very well-known subject in context of Lorentz invariant series. But if you actually get rid of this fundamental property of Lorentz invariance, then in principle, you can expect that you will also have a violation of a well-known procedure of constructing gauge invariant counterterms. It turns out that still these counterterms can be constructed in a gauge invariant fashion.
What does it mean, gauge invariance in this case? Because there's no Lorentz
invariance,
no general relativity. Sorry.
If you consider the class of background covariant gauge conditions, then one can prove that the structure of the renormalization will satisfy the requirements of BRST theory. So if you use background covariant gauge conditions, then
what does it mean what does it mean gauge invariance in this case? Because Lorentz invariance is broken down, general covariance is broken down. What is gauge invariance?
Just a minute. Three-dimensional general transformations. They are here. So
okay,
three-dimensional diffeomorphisms, they are local. That's why
yes,
we need...
I understand.
Okay, and now what we do, we just generalize this class of gauge conditions to the class of the so-called background covariant gauge conditions, which means that these gauge conditions, they start parametrically depending on the background field, and they are gauge covariant. They are covariant under the simultaneous transformation of both the quantum field and the background field. And if you have this property, then the counterterms can be derived in the covariant form as the sum of invariant structures. And this is actually the part of the whole project which I'm afraid I will not be able to really explain in much detail. Basically, it consists in the following sequence of steps. One step is actually based on the analysis of the cohomology properties of the corresponding nilpotent BRST operator, and the whole procedure of the proof that actually extends to the case of theories with violation of Lorentz symmetry, and even more also to the extension of non-renormalizable effective field series. Non-renormalizable in the following sense, that we don't have to restrict ourselves with the class of counterterms, finite set of counterterms. In principle, you can imagine that you have the theory understood in the sense of the effective field theory, which consists of the infinite set of terms in the Lagrangian, so that non-perturbatively it is some kind of non-local but expandable in powers in gradient expansion structures. And then you can show that even in this class of series, you can by using this background covariant gauge conditions, you can obtain the structure of divergences in the following form. You see the difficulty of the extension of the usual Bogolyubov-Parasyuk-Hep renormalization procedure in case of gauge series is the problem is the following, that you have original action of the theory, classical action of the theory, which is given by the sum of the classical gauge invariant term plus the BRS nilpotent BRS exact term, which has the form of the BRS charge operator acting on the so-called gauge fermion. And actually, all the details of gauge fixing procedure is actually contained in the construction of this gauge fermion. And then if your renormalization procedure is consistent, one should show that you have the structure of renormalization, BRST structure of the renormalization is the following, that separately you have the renormalization of the classical action by the chain of gauge invariant counter terms. And you also have some kind of non-trivial generically renormalization of the gauge fermion. The structure of this renormalization of gauge fermion is actually rather immaterial because in any case, the physically interesting objects like S matrix or expectation values of gauge invariant operators, they are independent of the choice of the gauge fermion if you stay on shell.
Does it mean that you became to use a BV technique? Does it mean that you
the idea is the following. You have to show that the counter terms, they always split in the gauge invariant counter terms to the classical action, which are the functions, local functions of the original set of classical gauge fields. Plus some kind of very non-trivial renormalization counter terms to the gauge fermion.
I ask you, do you use Bartalny-Vilkovitsky formalism in this case?
No. This is just first of all, this is the class of series with closed algebras. This is just the original BRST technique. I believe that it is possible also to extend it to full-scale BFE.
No, but Bartalny-Vilkovitsky formalism can be used for any theories. For example, for theories with closed algebra and independent generators.
Well, if look, if you have the closed algebra of your gauge transformations, then you do not need really the full-scale BV formalism. This is just the original BRST construction.
But
if you study renormalization,
the gauge fermion is just element of Bartalny-Vilkovitsky technique.
Well, yes, but this is also an element of BRST technique.
Okay, so
well,
but in BV, I think you can simplify. You don't need to discuss separately the renormalization of action and gauge fermion. Everything boils down just to BRST cogomology. The question is that in your case, you consider it not in the space of not necessarily Lorentz invariant functionals. But
just
still
a minute,
Maxim.
Maxim. The problem is the following: we expect that renormalization boils down to the renormalization of coupling constants in this S of phi, S of where phi. But because Bogolyubov-Parasyuk-Hep scheme will actually perform a complete chaotic mix-up. You will have local counter terms which will somehow be intertwining both phi and all the ghost fields that are sitting in the gauge fermion. This is a problem. You have to disentangle the renormalization of classical action and to ascribe this renormalization to the renormalization of the charges inside of this S. And then whatever happens with the gauge fermion, we just don't care. At least because what we have on shell is well defined. And this was shown that it is possible for there is a generic set of theories with generic closed algebra. With linear, I have to also to add that the generators should be also at maximum linear in the fields. If the generators are non-linear, again, unfortunately, this proof, we don't have this proof. Well, so I'm afraid that this, I cannot go into much detail of this step of the whole program. Maybe it would be more interesting to go over to concrete applications of this result. So what we have actually the class of Horava gravity models, which are projectable, and one can prove their renormalizability. So let us now try to analyze some in the lowest order in one loop approximation. Let us analyze this, say the properties of this renormalization, whether we will have asymptotic freedom. And it is interesting that one can prove the asymptotic freedom in 2+1 dimensional theory. And this runs as follows. In 2+1 dimensional theory, the action has such a structure. You have the only quadratic and curvature additional term here, in addition to the kinetic term quadratic in Kij. Then, well, we consider the projectable theory, n equals 1. Then one has to actually, you see, there are two non-trivial coupling constants in this Lagrangian, actually three, of course. There's gravitational, which is just like in gravity in Einstein theory. Then you also have non-trivial coupling constant lambda in the kinetic term and the coupling constant of quadratic in curvature term. It turns out that not all of them are essential. One can show that on shell, you have only two essential coupling constants such that their renormalization is actually independent of the choice of gauge conditions, the one that were actually used within this gauge fermion in the previous question that we considered. So these essential coupling constants are just lambda and curly G, which is the original Newton constant divided by the square root of mu. And so in this model, yeah, as we will see, G and mu will be running in different gauges differently, but this ratio will be okay. I will show this. Why is that? They enter the they have physical sense, right? You see, if you the counted term to the section will depend on the gauge, and the dependence on the gauge will be proportional to the equation of motion. Now, if you enforce the equation of motion, so put delta S over delta gamma equals 0, this will mean that this actually is different terms of this expression and counted. They will not be independent. They will become actually this the contribution only proportional to some combinations of the original coupling constants. And this combination are just essential coupling. They cannot, their renormalization should be, because if you consider go offshore, then renormalization of different invariant structures will be gauge dependent. Result in gauge dependent. Is it clear?
Suppose I just old-fashioned way will calculate the estimate, right? And I will have you move diagrams, divergences, logarithmic counting, and then I will just run the norm group for these three couplings. What will I see?
As matrix, you actually can look at this but it depends only on their nature.
Очень плохо слышно стало.
Да, вы, наверное, поверните микрофон, наверное, как-то отвернулся.
Yeah. Okay, I understand. So maybe no,
Я ничего не слышу.
so these are two dimensionless couplings basically, right? Yeah. Okay.
Слышно докладчика? Can you hear the speaker?
No.
Not very well. Not very good.
Подозрение, что там все в батарее.
Is it better now? No.
Yes, it is.
It
It is.
is?
Yeah, now it works.
Okay. Okay, so we are gradually. So how much time do I still have? I'm just wondering.
Well,
Because
roughly like 15 minutes together with questions, but you had many questions, so
So about 15
yes.
15 minutes. Okay, I'll try to do this in 15 minutes. Anyway, so what here is the choice of gauge. You see, this is background covariant gauge. It involves covariant derivatives here, covariant with respect to the background field. This is the choice of this gauge fixing matrix. And then we just apply standard Feynman diagrammatic technique and derive the renormalization beta functions of lambda and g. This is the answer. What is important here? Actually, this is a powerful check on the correctness of the obtained results. If you calculate beta functions separately for mu and g in one gauge, actually in the so-called conformal gauge, which is very different from this kind of a generalization of Lorentz covariant gauge. But of course, it is no longer Lorentz covariant. But it involves time derivatives of the Lagrange multipliers of shift functions. So it is interesting that if you consider this conformal gauge fixing, which is possible in 2+1 dimensional theory, and then in this quasi-relativistic gauge, you see beta functions separately for mu and g, they are absolutely different. You see here you have one type of numerator and here is another numerator. But if you compose out of these beta functions, the beta function of the essential coupling, they become the same. This is the way how this independence on shell gauge independence works. Here is the set of renormalization group curves. So what we found that there is at least one, actually asymptotically free UV fixed point, which corresponds to the value of lambda, which is about 15/14. This is a rather strange number. There is another point, but this is actually point in the domain of strong coupling. What separates these two regions? This is a range of lambda between 1 and 1/2. This is the range of non-unitarity. This is the range where actually this additional scalar mode becomes a ghost. This is to your question, Mika, that if you the ghost nature of this additional mode, scalar mode, it depends on the choice of this lambda parameter and the kinetic term of the Lagrange. It turns out that in this domain, This is a domain of non-unitarity. You have a ghost mode already at the classical level. So it's interesting that this asymptotically fixed fixed point, asymptotically free one, it exists in this unitarity domain of the theory.
And sorry, and what is unitarity? Like you define a norm and you show that it's positive, and it's also what SO3 times R invariant.
Well, even simpler, we just don't go to this group theoretic aspects of absence of ghost. We just have second order time derivatives in the Lagrangian, and or the squares of, you have a kinetic term, quadratic in the first order time derivative of the field, and the coefficient of this kinetic term is positive. This is just the definition of unitarity. And of course, you can have the problem with tachyons, that the tachyon part, well, the spatial gradients part, it can enter the game not in a good way. This is a problem of a low energy situation. In high energies domain, where you have the major contribution comes from the leading powers of the spatial momentum, the sign is okay. But in the low energy domain, you can get the problem that you have tachyon excitation.
But I guess what you are saying is that the energy is bounded from below, right?
Well, yes, the energy of in this high energy domain, the energy of this mode is positive.
But I would say that unitarity means something else, that you have actually a norm. And your symmetry operators are realized by unitary operators in that space.
Well, usually it happens that these properties of positive energy is related to the group theoretical notion of unitary representation, as far as I know.
Yeah, there is some
I
intuition.
believe there might be some exceptions, but I'm not such a big expert in the group theoretical representation aspects of this theory. Now let's try to do the same with 3+1, that is 4-dimensional Horava gravity. In this case, you have it's again projectable case, and in this case the Lagrangian, this potential term, it involves now either cubic in curvature terms, there are two of them, or quadratic in curvature, but containing extra two derivatives. There should be no ellipsis here. This is just a typo. This is the maximal set of marginal operators in this theory, which provides renormalization of logarithmic divergences in this theory. Of course, there can be also essential coupling constants of Einstein type and quadratic in curvature, but we are interested in the high energy part of this potential. So this is the full set of these invariant structures which provide renormalizability of this theory. So now we have actually 7 coupling constants. Again, between these 7 coupling constants, one can show there is only 6 essential ones. And to begin with, we were able actually to calculate the beta functions of the first 2 coupling constants, G and lambda, which sit is entirely in the kinetic term of the Lagrangian. And it was possible to do it by the usual Feynman diagrammatic technique. Although it was a very complicated calculation, but it still is possible. So I would not actually dwell on this part. And what the most interesting and what most important will be actually the renormalization, the construction, calculation of beta function for the rest of this coupling constant, nu1, nu2, nu3, nu4, and nu5. And for this, to get the result, it would be absolutely impossible to do it in the usual Feynman diagrammatic technique, because this is, I believe it's not even millions of Feynman diagrams, different types of Feynman diagrams, which would be impossible to calculate. So we use the so-called background field method. And the background field method is based on the proper time method, which means that you can express a one loop effective action in terms of the functional trace of the heat kernel of the operator, which is the inverse propagator of the theory. And if this propagator, inverse propagator, this is differential operator, which is of the so-called minimal second order type, that is, the derivatives are forming the covariant, the Lambertian in the external background field, that it's an external background metric of the theory, then one can actually construct for this heat kernel the well-known Schwinger-David expansion in the limit, asymptotic expansion in the limit of the proper time s tending to 0. And the coefficients of this expansion, they can be calculated, at least the coincidence limits of this coefficient, they can be explicitly calculated in terms of covariant structures which enter the definition of this operator, which are commutator, commutator of covariant derivatives acting on in the vector bundle, on the vector indices. This is just Riemann tensor. Then the curvature tensor in the fiber bundle of this generic system. And then one can show that the first three, at least in the four-dimensional case, the first three coefficients of this expansion in the coincidence limit, they are given by a very well-known expressions which are given here. This is a potential, P is a potential term of the operator. These are quadratic combinations of the curvature, quadratic in the fiber bundle curvature, the square of the potential term, and so on. And the divergences, one loop divergences, they're just given by the second Schwinger-David coefficient. Say in the dimensional regularization, this is just matrix trace of this David coefficients. The problem is the following, that in our case, we have high order derivatives. We do not just have box. We have high order derivatives. Moreover, these derivatives are not diagonal in the following sense. They are not just the power of this D'Alembertian. Well, in principle, this technique can be generalized to the case of high order derivatives and the non-trivial symbols of this operator, when the high order derivatives form some non-trivial principal symbol of the operator. And the way how these problems with non-minimality of the operator can be circumvented looks as follows. For example, if you have to calculate the one loop effective action for the theory with high order derivatives, but minimal ones. For example, you have the Lambertian to some high order power n plus potential term or terms with lower number of derivatives. Then one can calculate it like this. You just factorize this into the product of box to the power n. You have this term, which is already calculable by Schwinger-David technique, but then you have also additional term, which you expand in powers of this structure. And then you get, in principle, you get a non-trivial contributions, which are given by the so-called universal functional traces. You see, these structures, they lead to the quantities which represent inverse powers of the box acting on the delta function acted upon by covariant derivatives to any generic arbitrary order. And then the divergent part of these quantities will contribute to the total divergences of the effective action. And then the calculation of this universal functional traces that was first done in the paper, well, suggested by Jack and Osberg very long ago. And then this technique was developed in much detail in my paper together with Gregory Wilkowski about the same time. These divergences can be very easily calculated by just plugging here this expression. You can just again represent this power of the inverse box by the integral over the proper time of the heat kernel, then plug here the Schwinger-David expansion, and then you get the divergences of this expression in terms of Schwinger-David coefficients. So this is more or less doable, but only 2 minutes. Okay, I will try to skip the details. There is one more difficulty, You see that in our case, we have the problem that actually in Horava gravity, you have a big disparity in the power of time derivatives and spatial derivatives. So this is in the 3+1 dimensional case, this is a 6th order operator. And you have only 2 derivatives with respect to time. For example, the example of this operator, which arises, for example, in the ghost sector of the theory of the Horava gravity. This is a vector field operator, which has such a structure of high order derivatives. You see, they are not just powers of the Laplacian, 3-dimensional Laplacian. They have covariant derivatives whose indices are contracted with the indices of the fields on which they are acting. So there is additional trick which allows to perform the so-called dimensional reduction method in the following sense. You can actually express the one loop functional determinant of the operator of this form as reduce it to the 4-dimensional trace, functional trace. You can reduce it to the 3-dimensional trace, functional trace, but of the square root of the operator, which is just the spatial part of this operator. And then there is a regular technique how to expand square root of the operator in powers of the curvature. You see, this operator itself, this is a differential of the finite order in covariant derivatives. And square root of this is, of course, the pseudo differential operator, which is now the infinite series in powers of the curvatures and the structures which remind very much this universal functional traces that I just introduced above. So we derive the coefficients of this expansion. Then we actually we can check very easily that only the finite part of these terms will contribute to divergences, actually, because we know that these curvature structures, they are maximum to the cubic order in the curvature. And therefore, you can calculate this this finite number of these terms, but this finite number of these terms is rather huge. For example, you see this 3-dimensional functional trace of the square root of this operator has the structure of the sum of such universal functional traces. And the examples of these functional traces, they are given for 2 cases here. For example, you see this is the square root of the covariant 3-dimensional Laplacian acting on the tensor delta function in the coincident points. The divergent UV divergent part of this quantity is given by such a combination. Another example, covariant D'Alembertian to the power 3/2 acting on a similar tensor delta function at the coincident points is given by such a combination. And of course, to proceed with such combinations would be impossible without using the symbolic manipulation programs. We worked on Mathematica with the package, exact package, the so-called exact package. And the final results of all these calculations are the following: that we have the beta functions for the 6 essential coupling constants, which are, these coupling constants are given here. Say the first essential coupling constant is Newton 1 divided by square root of nu5. Then you have lambda that was already discussed before. Then the additional 4 coupling constants which are listed here, and for them we have the set of beta functions which are given in terms of enormously long polynomials and these factors which are already have some structures, polynomial structures also in the denominator. And these polynomials, they are Yeah, I'm just finishing. This is just a couple of more slides, and I am done. This is just the example of the maybe the longest polynomial that contributes to this beta functions, and of course the probability of mistake was very high. There are, however, very powerful verification checks that can make us sure that the results are absolutely correct. And this check is based on the main property and dependence of the essential beta function on the choice of gauge conditions. And so we have a two-parameter family of gauge conditions, and we can see that the results are absolutely independent of this generically just arbitrary parameters. Additional check was just the calculation of this universal functional traces by the method of spectral sum and the use of dimensional and zeta functional regularization when you have the three-dimensional space, if you take it as a three-dimensional sphere. And all these calculations has led to the results, similar results. Now, there are interesting properties of this very complicated beta functions. For example, there is a special point which is not a fixed one, but in which a big number, actually 3 beta functions, are exactly 0. 2 of them, 2 additional ones, are regular, but not 0. But they are not singular at this point. And at this point, which is given by these values of these parameters, values of the essential coupling constants, at this point, it's interesting that the Horava gravity action reduces to the so-called action in the presence of the detailed balance. This is a detailed balance version of Horava gravity. And this detailed balance version of Horava gravity is characterized by the fact that it establishes a kind of a relation between the quantum theories in D and D+1 dimensional theories. You can see that in this case, one can write down a kind of a Langevin equation in the framework of the Parisi stochastic quantization method. And you can see that actually this whole Horava gravity action reduces to the structure where you have the kinetic term plus potential term, which turns out to be just a quadratic combination of the three-dimensional cotton tensor. And as you know, cotton tensor is just the variational derivative of the three-dimensional gravitational Chern-Simons theory. So there is this is a very interesting property that might have some interesting prospects for further research. And now to the fixed points. There is a number of fixed points. It is interesting that some of them are really good candidates for asymptotic freedom. At the moment, we don't have actual analysis of the renormalization group flows because these flows are rather complicated. But it's interesting that there is a number of these asymptotically free points, asymptotically free fixed points, and there is also a number of additional fixed points which correspond to the value of the parameter lambda tending to infinity. And this limit is again very interesting in the context of the so-called non-relativistic gravity, which arises which is somehow related to Perelman-Ricci flows that was considered by people like Frenkel, Horava, and Randall. And this limit also has interesting cosmology implications considered by Mukayama and his co-author. So again, we have the set of such fixed points. And again, number of them, some of them are definitely candidates for asymptotic freedom, some of them not. And this is a property of them being attractive or not attractive in the direction of the lambda flow, the flow of the lambda variable. And this is my conclusions. I'm sorry for bringing over the admissible time. Basically, what we have, we see that Horava-Lifshitz gravity, non-projectable version of this model, kind of performs salvation of unitarity within local renormalizable quantum gravity theory with broken Lorentz invariance. Then one can perform Bogolyubov-Parasyuk-Hebb-Zimmermann renormalization if you work within the so-called class of regular propagators satisfying the property of positivity of the corresponding inverse propagator operators. One can prove the gauge invariance of UV counterterms in the class of background covariant gauge conditions. Then in 2 + 1 dimensional theory, there is definitely the property of asymptotic freedom at one concrete fixed point. And then one can use method of universal functional traces to calculate all the whole set of UV beta functions in the high energy limit of renormalization group flows for 3 + 1 dimensional theory. And there is a number of fixed points candidates for asymptotic freedom there as well. Thank you.
Thank you.
I thought that you raised your hand with a new question.
Are there any questions?
Well, I have a general question. The general question is just about well, what to take out of the talk, right? So, as I understand, the idea is basically that, first of all, about Horava-Lipschitz gravity, and in particular, that you can treat the gravity theory with Lorentz violation, and it can be normalizable, and everything works just as we, well, not just, but with specific adjustments, it works as a usual theory and so on. But do I have to sort of take out that in general, I have to expect that for Lorentz violated theories, everything, well, at least in terms of normalization, should work. For example, if I consider scalar theories, Lorentz violated actions, and so on. So where are the boundaries? Like, do I actually have to not believe in the Lorentz invariance principle anymore, or boundaries that, for example,
naively a priori violation of Lorentz invariance calls in question all this well-known conventional, to a certain extent commonplace statements about applicability of Bogolyubov-Parasyuk scheme. And naive statements, they are not complete. You have to check. This check has been done, and it was shown that for this particular class of models, everything is okay, that it is renormalizable, so on. And these statements, that there is a combination of rather non-trivial different aspects. One aspect, this is just the proof that power counting arguments, they have to be done more precise. Another is the statement about covariance of counter terms. This and the theory is very non-trivial in the following sense that you see, well, of course, this three-dimensional diffeomorphism, local gauge transformations, they are, on the one hand, they are simple, but on the other hand, they are immersed in this framework of Lorentz non-invariant spacetime theory. And the question is whether it will break standard statements done by people like Anno and many other people, beginning actually from Faddeev, Popov, and so on. It turns out BRST, Tutin, Batalin, Velkovsky, Voronov, Tutin, and all this analysis, they were done in the framework of Lorentz covariant theories. And it was not clear whether this extension to such class of theories would work. It turns out that it does. It's interesting that this BRST technique that I was very briefly just exposed the steps of this program. They are all these statements. They in a concrete model, they do not even depend on explicit counting, power counting of the analysis of this scaling dimensionalities, because these are very general statements. And then this was very interesting, at least you know, the way it turned out that it is. You see, when you can, for example, prove word identities for the generating function of the Green's functions for the effective action just in one line, this is a big advantage and big achievement, because the usual derivation, it takes a lot. But if you just generalize the notion of the nilpotent charge and introduce, for example, the sources in the generating functional for the Green's function into the gauge fermion and into this nilpotent charge, then actually this proof becomes, it occupies just a couple of lines. Well, I'm sorry, I could not really show how the details of this works. And then, of course, the method of universal functional traces. This was just a very, very strong, powerful demonstration how they work, because this method actually performs the resummation of infinitely many terms and actually makes the calculational procedure immensely more concise, rather than in the Feynman diagrammatic, usual Feynman diagram approach.
Okay, thank you.
Welcome.
So there is a question in the chat. So the question is how you can deal with the divergences coming from matter fields? From matter fields.
From matter?
Matter, yes. If unchanged, they will produce a covariant R² type divergences, and the scaling relations get broken.
Well, this general statement about BRST structure of renormalization, they will stay absolutely the same. As long as this matter does not violate the closure of the gauge algebra. For example, if this matter is such that the generators of gauge transformations become nonlinear, and it is no longer the representation of the linear group, then this is not extended to this class. But if this is a simple matter which falls into this category, then this is okay.
Yes.
Now, about asymptotic freedom, how matter fields will change this conclusion. No, this is absolutely open problem. We have just to include matter into the game and perform all these calculations from scratch.
Suppose you put matter like B in the top.
Yeah.
Then this will not work, right? Because if you integrate out matter, then you obtain R squared, R2.
Well, if you the infinite series of curvature. The question I did not get. What is it? The question whether the asymptotic freedom will be retained or whether the method will still work, because the BRST method will work also for effective field series.
I understood that
it will remain renormalizable in the framework of the infinite set of counter terms. So in the usual sense, it is no longer renormalizable because you have infinitely many higher order operators in the game.
so
Here we are talking about renormalizability in the usual sense. You just take in a given d dimensions, spatial dimensions, you consider the theory which has a 2d power of the curvature. Well, not the curvature taken to the power d, or the dimensionality of the different local structures up to 2d. And renormalization of this theory is just within this finite set of counterterms. You do not have extra.
Let me ask, can you couple in the usual the theory around or you should couple it also in the Lorentz non-invariant way?
Of course, you have to do it in the Lorentz non-invariant way. You have to introduce also higher order spatial derivatives also to matter.
Okay.
But then, of course, the question will arise whether this property of regularity of propagators will be retained. This is already the problem, the question which depends on the concrete choice of the model. You have to do it separately for all models.
Okay, there is addition to that question, but I don't know, maybe you can, I will
I
translate.
can say if you want. Do you
Yeah,
hear
yeah.
me? So, Andrei,
Yeah.
what I wanted to ask is the following. Imagine you have some matter fields, free matter fields, and they normal matter fields without modifications. And then you calculate vacuum divergences, one loop vacuum divergences, very standard calculation. And it gives you square of the wild tensor square, okay? Therefore, you get trouble because you square of the wild tensor has force derivative of time derivative of the metric. Now, then you get your ghosts back and so on. Now, if you actually, this calculation was done by Mazzitelli and Diana Lopez-Nazir, Diego Mazzitelli and Diana Lopez-Nazir. If you modify matter fields, then you get supernormalizable gravity, supernormalizable matter theory, because you cannot modify it only for vacuum contributions. You have to modify it forever. So for matter field sector, then, for example, in QED, you're risking to have theory without running of electric charge. And running of electric charge is something we can measure. So can you comment on this possibility?
Well, I'm afraid it's too long. To begin with, frankly, I do not have the answer to your question. I don't know.
Okay.
This
No,
is,
no,
this
no
is,
problem. No
this
problem.
is, this is too. You see, this is. One should be more specific, I believe. You cannot give the answer in general. So I'm sorry. Well, that's
No, no problem. No problem. Of course.
Okay, I think we should stop with questions because we are substantially over time.
Sorry for this. Yeah.
Okay, thank you for a nice talk.
Thank you. Thank you. I really appreciate your attention.